So next, I want to show how you at least formally can represent the inference problem in discrete Markov random fields in a form that will be accessible to standard software. So if you look at this title, ILP means integer linear programming. Who has heard about it before? Okay. So then let me start by saying what an integer linear program is. It is an optimization problem of the following kind. We want to maximize an objective function which is linear in our variables of interest, which I've here called mu, subject to linear constraints. So capital A is a matrix, mu is a vector, B is another vector, and all elements in this vector should be integral. So this is super easy to write down, super hard to solve in general. This is a NP-hard class of combinatorial optimization problems, and practically all combinatorial optimization problems can be rewritten as an integer linear program. There are also industrial solvers like Cplex and Gurobi that cost heaps of money and that are really good at solving this kind of problem. I would love to tell you that there's also, such and such GNU software or open source software to do the same. The sad truth is that on most benchmark problems, these industrial solvers are faster by a factor of 100 upwards. Okay. Now this number, I'm making it up. Yes? It's worse for some problems than for others, but unfortunately there is no good open source solver available. Okay, so this is a recognized standard form of an optimization problem, and if you have a combinatorial optimization problem to solve, a typical first step is to try and rewrite it in this form, because when you do rewrite it in this form, then you can invoke one of these programs and then see if maybe the computer on your table is even able to solve it. If you ask me how big a problem instance can these solvers address, then I have to give the answer, it depends. It depends on the hardness of your problem, or if we're talking about graphical models, on the loopiness of your graph. I'm quite serious when I say that there are problems involving just 50 random variables which are unsolvable, and there are problems with millions of random variables that are solvable. And some problems are just combinatorially harder than others. And a good example of a hard problem, for example, are constraint satisfaction problems. Or let me show you one. Eternity, I believe it's called Eternity 2. So this is a puzzle. Unfortunately, unlike a normal puzzle where you can see, okay, there is a piece of a face and a piece of a cloud and a piece of a wheel, and all these are cues which help you assemble the puzzle. These pieces here are very simple. And this means there are very many possibilities in which you can combine them. and there was an Eternity 1 puzzle for which a prize of £1 million or so had been offered if you were able to solve it within, I believe it was 1 or 2 years. And actually, two mathematicians did manage to solve it with the help of a big computer. I'm not sure if they did it before or after the deadline, but in any case, these two mathematicians were hired to then develop the second version of the puzzle, in which these mathematicians made sure that there were not the kind of combinatorial flaws that made solving the first puzzle possible at all. And this has a mere 256 pieces. It's not much, right? 256 pieces, each piece has 4 sides, and now it's been out for a few years, this puzzle, and it's still unsolved. Okay? So this would be an example of a problem with relatively few, it's relatively small, and yet it's completely unsolvable. Nobody in the world has been able to do it, even though there's a big incentive, in terms of money, fame, whatever matters to you.
The solution exists, so they
supposedly. Supposedly the solution exists, yes. No, I also believe that the solution exists, it's just that the search space is too big. Yeah? It was, I believe, £2 million. No. There was a time. There was a limited time. There was you had to solve it within. It was something like 2 years, I believe. The 2 years are over, but even now, even after the deadline is closed, still nobody has been able to solve it. Yeah? You can still earn fame now at this point. Okay. Good. So let's take our Markov random field maximum a posteriori, our map problem, and bring it in this form. That's the content of the next half hour. Without loss of generality, we consider only pairwise MRFs. So pairwise means that no factor has more than 2 neighbors. So if I'm taking our standard Cartesian model here, this is pairwise. And if I'm now starting to add extra edges here, this is still pairwise, because each factor only has 2 random variables in its scope. But if I did enter a factor, which would depend on 3 random variables, this would no longer be pairwise. However, in the exercise, you have seen, or you will see by tomorrow, that actually every discrete Markov random field you can rewrite as a pairwise Markov random field, which is why we will stick to these pairwise discrete MRFs for now. Okay. Now, I have 2 kinds of factors here. I have the unary factors, which I'm writing here. These are psi I for random variable xi, and we have the pairwise factors, where ij should be in the edge set of my graph. So v were the vertices of the graph, and e is the edge set in my graphical model. Okay, and if I'm now taking the negative logarithm of this, then the map problem here is to say we are looking for the configuration X, which will minimize our energy. we go. And the trick is to now indicate, to introduce so-called one-hot indicator vectors. Meaning, if I have an indicator vector associated with variable I, then this checks if a random variable xi, if discrete random variable xi is in state k. And k now comes from a finite label set. And by one hot, I mean that if I sum over all k possible labels, then I should have a 1, and each individual element, as we see here, so capital I is the indicator function, is binary. It's either 0 or 1. Good. And now these, I'm calling this indicator vector because I could stack them. Yeah? So I can later on define a huge vector mu transpose, which starts with mu1, the first possible label for variable x1, and it continues with the second possible label for random variable x1, and then eventually we get to the nth random variable and the elf label of the nth random variable, and leave some space. We will add more to this indicator vector. Because these were the indicator vectors for the unary factors, I also want indicator vectors for the pairwise factors. So I also want mu ij, which depends on k and on labels k and l, associated with random variables xi and xj. And this is the indicator function that xi equals k multiplied with the indicator vector that xj equals l. And you see these elements I can also append to my huge vector mu. So I can add here mu 1, 2, 1, 1, x1, x2. So with this term, I'm indicating if my random variable x1 is in state 1 and random variable x2 is also in state 1, and the final entry would be mu n minus 1 n, and let's say here we check if each of them is in the elf state. This is a capital L here, script L. Okay. So if we associate a random variable with every pixel, then this is going to be a huge vector. It will have a zillion entries. Okay, this is my overall indicator vector, and I can now rewrite the energy formula that you see at the top of the screen here. So the energy is given by, I can sum over the random variables I and over the possible labels k. As before, I and j should be neighbors in my graphical model. And then I sum over the possible labels k and l. Okay, that is my energy function. So I've not done anything yet other than previously I was summing only over the random variables, and now I'm summing over random variables and states, but only one of these summands is multiplied by 1 and all others are multiplied by 0. So this does not change anything from the energy function that we saw previously. However, note that this is still a function of x. And now I want to turn it into a function mu. So my map problem, I want to write it. So here I had a minimization over x, and now I want to minimize over mu. And this time I have omitted the dependence of the mu's on the x, because you see this was anyway redundant. Here I had written that mu I, mu j is associated with xi and xj. So this is why in this formula, in this latest formula, I have now omitted the x's, the x at all. But if I only write it like this, there could be a problem. So for example, if I represent, let's say I have just two possible states for random variable x1 and I have two possible states for random variable x2, and I'm now indicating which state I'm in using these indicator vectors which each have two elements. Then I could say, for example, x1 is in the first state and x2 is in the second state. but my second random variable, unless I tell it so explicitly, it could decide that it prefers to be in the state that I've indicated here, which is not compatible with, so we have, here actually we have two incompatibilities. Let me reduce this to one. So let's say, here this is compatible, this is fine, but here I have a clash, in the sense that my vector mu1 is not compatible with my indicator matrix mu1 2. Okay, because the first mu1 tells me that I want to be active somewhere in this row, which is not happening. The second condition is fulfilled. So I need to enforce that explicitly. I need to make sure that the system can only be in valid states. And a valid state would be this one in this case. And well, the reason that the system does not by itself decide to be in a valid state is because if I just write the summation as I did up here, then this bivariate or this binary, this pairwise term would simply pick the state which has the lowest potential energy, and the unaries would pick the state which gives it the lowest potential energy, but these need not be the same state. Okay, so in order to enforce this kind of consistency, I have to do the following. I have to say that if I sum over all labels L in mu ij kl, then what should be the result? So mu I, yeah, go ahead.
So I would say, so if we sum over all S and L was a fixed one for X in the above one, then I would say it's mu as a function of K times X.
X is no longer there.
Yeah, but yeah, if I plug it in as you did above,
Yeah.
then it's the overall assumption for the limits of X.
It's the overall assumption for the what? For the
limits of X.
For the limits?
Yeah, because we sum over all L, and L was above the function of X, and we said it's equal to Xi or something like that. So I would say it's also times the limits of X. I don't know whether that one is 1.
So the formula here is correct, only I'm not sure why, if we should talk about limits here, because so K and L encode the state of these random variables, and in the example that I've drawn here to the left, I had two random variables involved, and each of these had two possible states. And what this formula is telling me that, for example, here I am summing over the states of the second random variable. So no matter what state my second random variable is, I want the result to match the unary. Yeah. So what it says is that the sum of this and this should match this, which is true, because 0 plus 1 gives 1. And the sum of this plus that should match this one, which is also true, because 0 plus 0 gives 0. And vice versa. So the same kind of constraint also needs to hold the other way around. The sum of these two should give this, and the sum of those two should give that. And the reason that we need these constraints now is because previously we had always worked with the states of the random variables itself, and then consistency just followed. Yeah? So we started by defining what state a random was in, and then as a consequence we got out the indicator vectors. But now that we don't have the states x anymore, we only have these indicator vectors, we have to make sure that these are consistent amongst each other. Okay, so we need this to ensure consistency between the unary and the pairwise indicator vectors. Okay, and in addition, we have that so by the way, now it would be a legal solution to set everything to 0 that would incur, let's say these psi's are all positive numbers, so from the energy minimization point of view, it would be attractive to set all indicator vectors to 0, which would be a consistent solution according to this formula that we have here. So we have to force the system to be in some state. Okay, and I can force it to be in some state by saying that summing over all states k of mu I k has to be 1. Now, if I use just this formula, perhaps this would like to put some entries of my vectors mu, let's say it would put one entry to minus 0.5 and the other to plus 1.5, and then the sum would be 1. That's also not desired. We want these entries to be integral. Yeah, so I have to add that mu I of k should be either 0 or 1. And have to impose the same condition for these pairwise indicator vectors. They should also be integral. Okay, now we can look at this overall. And look at the structure of this optimization problem. We have an objective that is a linear in mu, where mu is now this huge vector composed of everything. You see, I had written that mu transpose equals, it's just a collection of all indicator elements that we have all together. Yeah? So my objective function is linear in mu because I take elements of mu and I multiply them with potentials that are given. I assume that these have previously been specified. And I have constraints that are also linear in mu, these two at least. And this together already tells me that I have a linear program, or LP, which is convex. It's a convex problem. But unfortunately, I also have these integrality constraints. Yeah, so those ones here. And together with these integrality constraints, this is an integer linear program, or ILP, which is non-convex. So previously I argued that an integer linear program should have the form that we maximize C transpose mu. So this is fine. Yeah, max or min is the same. I can just invert the sign of C. This cost vector C would somehow comprise all the psi's. This is also fine. However, I had said that these linear constraints should be an inequality constraint. So in other words, the maximization here is something I can see on the left-hand side. Yeah. So if I just change the sign of C, then max or min is the same thing. Mu integer is also fine. That's what was written here. We still have a bit of a problem in the sense that here's an inequality and there are equalities. Does anybody have an idea how we can formally write an equality in terms of inequalities? Yeah.
I just would do it in a way that I use the exponential function, make sure that using what is the part of the argument of the exponential function, make sure that the limits of that is always not depending on what I'm multiplying with the exponential function below b.
So I think you are thinking of a barrier function, but that would be nonlinear. There's something simpler we can do here, yes?
You can make two conditions, one out of one, just adding a minus and
Exactly. Yes. So I can write, what you're saying is that I can write that A times mu should be less than B, and minus A, or you also want to say that A times mu should also be no less than B, and then these two taken together tell me that A mu should be B. And if I only want inequalities pointing in the same direction, then I can rewrite the one at the bottom here as saying minus A mu is less than or equal minus B, and then I have a less than or equal here and less than or equal there. Yeah? So, or if I want to summarize it as matrices, I can say that here I stack these equations, A and minus A, multiplied with mu gives B and minus B. Or yes. So so the question was, can the solver not handle equalities directly? Many solvers can, but internally it will, or it may do, depending on the algorithm it chooses, do something like we've seen here. Yeah? So actually there are various forms of, there are 3 conventions about how you write a linear program, and you can translate every convention into any of the others by using a trick like this one. I just wanted to be explicit here because I wanted to get exactly the form that I had previously said codifies an integer linear program. Okay, So bottom line is, if we remember the trick on the right-hand side, then the thing in the big black box here is indeed an integer linear program, and the consequence is that whatever graphical model I have, so no matter if I have a tracking by assignment model, or if I have a grab cut problem, or a stereo problem, or an image denoising not, because here we used continuous random variables. So whenever I have a graphical model involving only discrete random variables, then I can always rewrite it as an integer linear program and give it to this Cplex Ogorobi solver. You will also see in the exercises that depending on the problem that you're trying to solve, this will actually work only for tiny problem instances, which is why we want to talk about this for a few more weeks. In the coming weeks, we will look on the one hand at approximations, and on the other hand, we will look at algorithms that exploit specific structure in the problem. So, for example, if your graphical model has the shape of a tree, or if you only have a binary pairwise Markov random field which fulfill a particular condition on these pairwise potentials, then you can make use of a max flow min cut algorithm. Okay, and then this brings you from completely unsolvable and NP hard to algorithms that are solvable even to global optimality in just polynomial time if the model has specific structure. Okay, so there's the program for the next weeks, and we meet again tomorrow.